Now we're going to talk about acids and bases. So we have cells in our stomach forms hydrochloric acid. This has various things. We as humans don't necessarily need this. We don't really need a stomach, but it does various things. Kills unwanted bacteria, so it makes our food a little safer. But of course, we cook our food, so we can do this outside of our bodies as well. And it helps break down food because of the caustic environments. It activates enzymes to break down the food. But sometimes this can go back up your esophagus. It can create a condition called acid reflux or even gastroesophageal reflux disease, also known as GERD. So uh, you can get rid of mild cases by neutralizing the acid. So so some things like saliva has the bicarbonate ion in it, or you can have antacids that contain hydroxide and or carbonate ions. Some antacids used to have bicarbonate ions in them, but that's sodium bicarbonate, and that increases your salt intake. So those are not typically used anymore. And mentioned before, GERD is a chronic condition, and there's various causes of this, and much of it sometimes is the damage to the sphincter. There's several sphincters in your body. One is from your stomach to your esophagus, and if that does not close properly, then this can cause GERD, and uh, and this can be diagnosed in the various ways. So some properties of acid: they taste sour. So like we mentioned hydrochloric acid, and I'm sure everyone in his or her life has vomited at some point in time. And what is the taste of stomach acid like? It's a very sour taste. So the like think of a lemon when you drink like pure lemon juice, so that kind of sour flavor. That's an acid. That's our tongue has chemical sensors on it, and the sour flavor for us is acidic. It can dissolve many metals as well. Acids can dissolve metals. The ones that acids can't, or at least not easily, they're the expensive ones, right? So gold, silver, platinum, copper. You can get those. So some will dissolve in nitric acid, but not hydrochloric. And you can get really noble metals like gold and platinum to dissolve in aqua regia. That's a combination of hydrochloric and nitric acids. It neutralizes bases, so acids taste bitter, bases taste sour, and then you get, well, we'll learn later about salts. Salts are the combination of acids and bases. And does salt, sodium chloride, table salt, does it taste sour? Does it taste bitter? No, it tastes salty. It's a new thing. And it changes litmus red. Acids do. So here's some common acids. Hydrochloric acids already mentioned. Stomach acid. It's also known as muriatic acid. Used to clean metals, make food, or refinery primary. Okay, I already mentioned stomach acid. Also, one of my favorite activities, used in swimming pools. So you can use hydrochloric acid in that. Sulfuric acid, so also known as battery acid. Biggest use for this is fertilizer. So also you can see nitric next to that is also fertilizer. So the second largest thing that we make as human beings is, well, as far as our chemical industry is concerned, is fertilizer. Number one is transportation fuels. Number two is fertilizer. Fertilizer is huge because we've industrialized our agriculture, and so we make lots and lots of fertilizer. And so sulfuric acid combined with ammonia to make ammonium sulfate. That's a very common fertilizer, for instance. And nitric acid is also it's a primary fertilizer, but also used to make explosives. So nitric acid is very dangerous from this. So, for instance, TNT, trinitrotoluene. The way that you make TNT is you take toluene and you mix it with nitric acid, forms trinitrotoluene. And nitroglycerin is another one. And the way you make nitroglycerin is you mix glycerin with nitric acid. So nitric acid has a tendency to make things go boom. Acetic acid, this is a primary component in vinegar, and also used in plastic and rubber manufacturing. Citric acid, this is found in foods. You can also use it too as a buffer. Carbonic acids, so this is in carbonated water. Water reacts with carbon dioxide to form carbonic acid. Our bodies also use this to transport carbon dioxide out of our cells to our lungs. Also, well, our bodies also use it for buffer, which we'll talk about in future chapters. Hydrofluoric acid. So this stuff scares me. Hydrofluoric acid. It's you can't feel it if you get it on you. It's a surface anesthetic. So, but it as it goes on, it's bone seeking. So this stuff you can get it on yourself. It can start going through your it can start absorbing through your skin and eventually eating your bones, but sometimes you don't feel it. So I'm kind of scared about this stuff. Used a lot for metal cleaning and glass cleaning and frosting. So if you ever seen like decorative glass and you see it's got this white stuff on it, that's made from hydrofluoric acid. But like mentioned before, very often used in metal cleaning. Phosphoric acid used quite a bit in making fertilizer because one of the primary nutrients for plants is phosphorus. So it's potassium, phosphorus, and nitrogen. So ammonia is oftentimes used for nitrogen, as is nitric acid. But phosphorus is also big for plants. Used as a buffer and also in beverages. So things like Coca-Cola have phosphoric acid in them. So the structure of acids, and this is a binary acid, so two things, two atoms. And so like hydrochloric acid, you have a hydrogen attached to a nonmetal, and it's easily popped off. So oxyacids have hydrogen attached to another oxygen atom. So you can see here sulfuric acid and nitric acid. They have the hydrogen attached to an oxygen atom. And carboxylic acid, so as you study more organic chemistry is the chemistry of carbon. This carboxylic acid group, the COOH, that is the carboxylic acid group. And that is the hydrogen. And the first hydrogen in this formula is the one that's acidic. So it tells you, so being acidic, we'll learn about this later, but not every hydrogen is an acidic hydrogen. The acidic hydrogen is the one that's relatively weakly bound, and so that's the one that'll pop off. The hydrogens attached to the carbons are not acidic, but the hydrogens attached in the carboxyl group, or carboxylic acid group, that is an acidic hydrogen. So mention acids, let's talk about bases. So bases taste bitter, and there's a category of chemicals called alkaloids. These are plant products. Alkaloids tend to be poisonous, and generally speaking, humans don't like bitter flavors. Humans also are not supposed to like sour flavor either, but many do like sour flavor. So things that are poisonous. So caffeine, for instance, is an alkaloid, and it's extremely poisonous. And so is nicotine, cocaine. These are all alkaloids, and they are extremely poisonous. But that's why if you take these, hopefully not in cocaine, but like caffeine is in really low doses. So meaning like a heavy cup of coffee is like 100 milligrams of caffeine, and so that's not a lot. 100 milligrams is not a lot of substance, right? And compared to other things that we take. We like sugar we take in the grams or tens of grams, right? So sugar is not particularly toxic, but caffeine is. Bases also feel slippery on our skin. So not just because something is slippery does not mean it's basic or alkaline. So the word alkaline and basic mean the same thing. So motor oil, for instance, is slippery but is not an acid or a base. Sulfuric acid. It's an acid that is slippery, but obviously that's not a base. The reason why bases feel slippery, and this is on your skin, is because bases add negative charge, and acids work by adding positive charge. So bases add negative charge, and adding in biological surfaces they're all negatively charged. So adding negative charge expands the electron clouds of the things around it. It creates that. And here I am rubbing my fingers together. You can't see me. It creates that feeling along a biological surface. It turns litmus blue and also reacts with acids to form salts. So some common bases: sodium hydroxide, also known as lye, Lye. Used quite a bit for petroleum. I already mentioned that the number one thing that we make as the human race, as far as chemical stuff with our industry, is fuel. We make transportation fuel. Number one is fuel. Number two is fertilizer. So uh, sodium hydroxide is used quite a bit to make fuel. Also used to make soap. So every single fat, the vast majority of fats that are found in plants and animals here on Earth are triglycerides. So three carbon glycerin and then fatty acids attached to that triglyceride, and or that I should say that glycerin. The whole thing makes a triglyceride. For making soap, you take lye and you mix it with a fat, and it rips apart that triglyceride. You get glycerin pops off, and then you have the soap, usually the sodium, and then whatever fatty acid you have in there. So Castile soap uses plants, and then most other soaps use some sort of animal fat, and also used for plastic manufacture. So various things, and potassium hydroxide next, also mixed for plastic, especially can be used in latex. But potassium hydroxide, another very strong base, like sodium hydroxide, used for various things: cotton processing, electroplating, soap production, batteries. So potassium soaps, they tend to be more the liquid kind of soaps. Oh, and batteries. Potassium hydroxide is found in many alkaline batteries. Sodium bicarbonate, also known as baking soda, used to be used as an acid, but not as much anymore. It can be used as a source of CO2 for like things rising, like anything from if you want to make soda bread, for instance. That's made from baking soda, and you can use various things like the foaming agents and helping things to foam, and things like yoga mats, and those can be used bicarbonate. But there's other things that you can use, and so it's not just limited to bicarbonate. But I'm just giving you an example of what it can be used for. Sodium carbonate. This is also known as washing soda. So used quite a bit for glass, and this is decorative glass. So the ancient Egyptians are the ones that figured this out. You take washing soda and you mix it with sand, silica sand, and you can melt it easier, and that's usually that makes the decorative glass. And soap manufacturing, sodium carbonate. For instance, there's a product called OxiClean. That's the primary component of OxiClean. Is this? It's just a very common laundry detergent in general. Also, and for dishwashing detergents as well. Ammonia. Ammonia is used quite a bit, especially with fertilizer. So it's really big use is to make fertilizer. Also for explosives, because ammonia is used to make nitric acid. The way you make nitric acid, you take ammonia and you burn it, you oxidize it, and then you mix it with water, and then you form nitric acid. So that's the way you make that, and really ammonia synthesis. So ammonia synthesis is what allowed World Wars I and II to happen. So if you want a connection to history, in Germany in World War I, they've developed how to using the Haber-Bosch process to make ammonia from natural gas and air, and at the time, Britain was the primary naval force in the world, and And the nitrate source for the world at that time were mines in South America. And the Brits thought, like, oh, if we blockade Germany, this war will be over very quickly. And it turned out that that since Germany was making their own ammonia using their chemistry know-how, it allowed them to continue on and actually fight and continue fighting in World War One. One of the ways to make ammonia, use a catalyst, and the catalyst turned out to be from Sweden. And it took us to about the 1970s to figure out that the catalyst from Sweden, the iron ore from Sweden using the catalyst, was because of potassium and aluminum impurities in the ore. But Sweden was neutral in World War II, provided that they gave the Third Reich ore so they could make the ammonia catalyst to continue with the war machine of Germany. So it's interesting how politics and science and history are very intertwined. So, and that it's also amazing that something that ammonia synthesis is what allowed, among other things, so ammonia synthesis and also the invention of antibiotics. Those two things have greatly allowed the population explosion that happened in the beginning of the 20th century, and then again that wonderful thing that has fed the world has also caused great destruction as well. So it's interesting how there's both good and bad that can come from these things. So which property is not associated with an acid has a bitter taste? Acids taste sour, bases taste bitter. So definition of acids and bases, I'll start with the simplest definition, the Arrhenius definition. You throw something in water, it forms hydrogen ions. And then bases form hydroxide. The better definition that we're going to use quite a bit in this class is the Bronsted-Lowry, and that is an acid as a proton donor and a base as a proton acceptor. So that's what we'll kind of go at the level here. There's also Lewis acid and base definition, where a base is an electron donor and an acid is an electron acceptor. So that's Lewis base theory. But the best way to think of it in this class is the hydrogen donor for acid, hydrogen acceptor for base. So for instance here, the Arrhenius acid, when you throw hydrochloric acid into water, forms hydrogen ions. And you can use hydrogen ions and hydronium ions, the H3O+. You can use it interchangeable in this class. We're not entirely sure if it is free hydrogen ion or if it's free hydronium ions. We think it's hydronium, but the thing is how can we tell? We do that by simulation, but we have no real spectroscopic way. Sorry as I fumble my words. Spectroscopic way of observing this, though, because if a hydrogen ion is just a proton, it doesn't have any electrons. We can't really probe the electrons around it to determine that. So it's kind of this is something we may never know, to be honest with you. It's just at the limit of our knowledge to be able to tell. So the hydronium ion, and it well, it says here they cannot exist in water. I know, I said that. Well, the truth of the matter is we don't know. We don't know if there's any free of them floating around in solution, and like I said, we know this by simulation, but I mean that's not really true data. So, but you can model it either way. So it forms hydronium ions, and that's the hydronium ion there. Arrhenius definition, still a base. Substance that produces hydroxide ions in an aqueous solution. So sodium hydroxide breaks apart to form sodium and hydroxide ions. So and acid-base reactions, the hydrogen ion reacts with the hydroxide ion to form water, and you get a salt. So here, this one, you have hydrochloric acid plus sodium hydroxide base, makes sodium chloride salt and water. So that's what you're going to get when you mix acids and bases. You're making water and salts. So Bronsted-Lowry is a little bit better in terms of theories and description. and it says that there is the proton donor, proton acceptor, proton donor being acid, proton acceptor being base. So acid is the donor, base is the acceptor. And looking at the reaction here, so HA acid plus base is in equilibrium with negative anion acid and then hydrogen attached to the base. So, and the acids are hydrogen donors. So anything that has a hydrogen could potentially be an acid. And for instance here, for hydrochloric acid, dissolving in water, the hydrogen chloride, that is the acid, and that is giving its proton to water. So HCl goes to Cl, and H2O goes to H3O. So HCl is losing a proton, water is gaining a proton, HCl is the acid, water is the base. And the bases are hydrogen ions acceptors. So in this case, ammonia, NH3, is a base, water is the acid, because NH3 goes to NH4, it's gaining a hydrogen, H2O goes to OH minus, it's losing a hydrogen, that means it's an acid. And so proton donor, proton acceptor. So then this you can see there's water. Water is weird. It can act like an acid, or it can act like a base. So water is a special thing. We call this property being amphoteric. That means it can be both an acid and a base. Water is not the only amphoteric substance. Amino acids, for instance, are amphoteric as well. But water can be an acid or base depending on the environment it is in. So Bronsted-Lowry acid-base reactions, the reversible reactions as follow. And these reversible reactions can go in both ways. So you have hydrogen attached to the acid and then the base in equilibrium with the anion from the acid and then the hydrogenated base complex. But then it can go the other way around, where in the reverse direction, you can see that the bottom here is just the equation reversed, where you have the anion from the acid and then the hydrogen base complex is in equilibrium with the acid, the original acid, and then the original base. So this is known as the conjugate pairs. So the conjugate pairs of that. So you have ammonia comes to ammonium, then you have the base, and then ammonium NH4 plus is the conjugate acid. And then water is the acid, and then sodium, I'm sorry, I even said sodium. Hydroxide is the conjugate base. So in the other direction, hydroxide is the base. So here again with the ammonia and water. In the forward direction, ammonia is the base. In the reverse direction, ammonium is a conjugate acid. Water is the acid. In the forward reaction and the reverse reaction, it is a base, the conjugate base. So which pair is not a conjugate acid-base pair? It's B because the oxygens have changed. Notice the other ones that's losing a hydrogen. This one here, the oxygens have changed. These are just two different acids, sulfuric and sulfurous acid, respectively. So a strong acid means strong electrolyte. So you throw a strong acid in water, it just completely breaks apart. Same thing with strong base. Weak acids are weak electrolytes. So there's an equilibrium, and the weak acids, they prefer to stay molecular. Only a small part ionize. Same thing with a small base, small base, weak base. Only a little bit of it ionizes. And many bases are ones that contain nitrogen in them. So ammonia and substitute ammonia. We mentioned alkaloids before. Those always have nitrogens in them. And many plant-based things there, and many the amines are organic compounds that have nitrogen in them. Those are all bases. So things like, and once you hear the words amine, you'll start seeing them other places, and you'll be surprised. Words like amphetamine. So amphetamine is an amine, and amphetamine is a weak base as well because it has that nitrogen in it, and it's a weak electrolyte. So strong acids, they just break apart. You can see here the hydrochloric acid, throw it in water, it just completely breaks apart and gives its hydrogen ions to the water. And here are the strong acids, and what I actually recommend you do is you just memorize them. So hydrochloric, hydrobromic, hydroadic, not hydrofluoric, so remember that, not hydrofluoric, nitric, perchloric, sulfuric. And only the first hydrogen on sulfuric. The second hydrogen, so HSO4 minus, is a weak acid as well. So anything that's not on this list is a weak acid. So keep that in mind. Weak acids, these prefer to stay molecular. So like hydrofluoric acid prefers to stay molecular, doesn't ionize as much. It ionizes a little bit, but likes to stay together. Why is hydrofluoric acid? Why is it a weak acid, not a strong acid? Well, because it's got a very strong hydrogen bond, and it'll bond with itself, and it tends to dimerize, and then that dimer tends to like to hang out together rather than break apart. It tends to kind of exist together and not ionize as frequently. So here are some weak acids, but it's pretty easy. If it's not a strong acid, it's a weak acid. And you can see there's diprotic, and there's many monoprotic ones, but then there's diprotic. That means more than one hydrogen that's acidic. And you can have triprotic. You even have tetraprotic. EDTA, H4-EDTA, so ethylene diamine tetraacetic acid is a tetraprotic acid. So you have many protons. So how strong an acid is, it's determining how big the equilibrium constant. So the bigger the equilibrium constant, the stronger the acid or base. Or you can look at it as the smaller the equilibrium constant, the weaker the acid or base. So, and the attraction, there's a very weak attraction between hydrogen ion and the anion, conjugate base anion, and a strong acid. Weak acid, though, there's a very strong attraction. And the Ka is the acid ionization constant. In this reaction, you have acid, generic acid, plus water, reacting for a hydromium, and anion. And then these products over reactants, and water is a liquid. So that means that the Ka is the hydronium anion over the acid concentration. And you can equate it to a hydrogen ion if you want. So I prefer that way just because it's one less thing to write down. So here are various Ka values for various acids. So consider the three generic weak acids. The images show here represent the ionization of each acid at room temperature. Which one has the largest Ka? It means which ones is going to break apart the most, and the middle one is the one that breaks apart the most. It has the highest Ka. So which acid is stronger? It's the one with the higher Ka. So water will also autoionize. Remember, water is amphoteric. It's an acid or a base, so it'll react with itself. And the degree that it self-ionizes is to 10 to the minus 7 molar at 25 degrees Celsius. This is the concentration of hydronium times the concentration of hydroxide together. This is known as the ion product of water, or the term Kw. And the Kw for water is 1 times 10 to the minus 14. So that means that whenever there is hydroxide or hydronium ion present, the combination of these together, multiplied together, has to equal 1 times 10 to the minus 14 at 25 degrees Celsius. If you change the temperature, Kw changes. So, but this shows the inverse relationship between hydronium and hydroxide. And same thing with acid-base solutions. So we'll get to pH soon, but if the hydronium and hydroxide concentration is the same, it's a neutral solution. Acidic solutions have more hydronium than hydroxide, and basic or alkaline solutions have more hydroxide than hydronium. So, and on most commonly, pH at 7 is neutral, pH less than 7 is acid, pH greater than 7 is base. Now, the hydronium concentrations of 3 solutions at room temperature are as follows. Which solution is acidic? It's that one there. It's going to be greater than 1 times 10 to the minus 7. So oftentimes use the pH. pH is a logarithmic scale, and it's the minus log of the hydrogen ion concentration or hydroxide ion concentration. And as I mentioned before, pH 7 is neutral, less than 7 acidic, greater than 7 basic. And you can flip back and forth between pH and hydronium or hydrogen ion concentration by 10 to the minus pH. So that's the anti-log function of sorts. Kw still holds at 25 degrees Celsius. So here are some common pHs of things. And you can see most foods, most consumables are actually, they tend to be acidic in nature. Rainwater, you can see, you'd be surprised, water is not pH of 7 because of carbon dioxide. So carbon dioxide at the atmospheric pressure, well, the 400 or so parts per million of carbon dioxide in the atmosphere, this saturates the water coming down, and it has actually a slightly acidic pH. And you can see various things. Human body is actually pH slightly alkaline, but we're pretty close to 7, close to neutral, but we're very slightly alkaline. So the pH number implies, well, first of all, one pH unit means a factor of 10 in magnitude. And we usually go from 0 to 14. So log of 1 is 0, for instance. You can have negative pH, and you can have pH greater than 14 as well. So, so one thing though, water is 55.6. Pure water is 55.6 moles per liter. So it's harder to get more concentrated than that. So you're not gonna. You can get 10 molar for some things, but it's going to be hard to measure pH greater than -1, or I say more acidic than -1, or higher than 15, just because of because concentration is amount per volume. There's just no more amount you can put in to the volume. And also for sig figs, the sig figs are displayed following the decimal point. So the pH of 3.00, this has 2 sig figs. So keep that in mind when you do sig figs with your calculation. Even if it was 12, it was 12.00. 12.00 is still 2 sig figs. POH is just like pH, but it's the minus log of the hydroxide ion concentration. And the pH plus the POH also equals 14. This is just the same thing with the KW. So this is just the, because hydroxide times hydrogen ion concentrations equals KW. So then you take the minus log of both sides. That means that that the pH plus the POH is going to be 14. So if you do the rules and the calculations for that. So a combination of these equals 14. You can do this by addition with the logarithms, or you can multiply together. I prefer to do addition, so I like this way better. And pK, this is the strength of the acid and the base. So rather than using the Ka, you can use the pKa. pKa is just the minus log of the Ka. And the pKb is the minus log of the Kb. So, then it just, you oftentimes, rather than looking up Ka values, you can look up pKa or pKb values. That's a very common way to find things. As the pH of a solution increases, what happens to the acidity of the solution? It decreases, because higher the pH means fewer hydronium ions and more hydroxide. So the hydronium ion and pH of a strong acid, and these come from, well, the acid just breaks apart, and it shifts that equilibrium very far to the right, meaning it just the acid it almost just basically completely breaks apart. And that means that the autoionization of water is really just negligible. So the acid concentration is just concentration of the acid. So find the pH of a weak acid, though, is a little more difficult because it involves partial ionization. So from this, we have to look at the equilibrium values. And one of the ways to do this is to set up an ICE chart, ICE, initial change equilibrium. Then you have to input the ICE chart and then fit that in for the equilibrium expression, and then calculate your value. So meaning like the extent of reactions. Look at the extent of reaction value. There are other videos that explain this. This video is more for conceptual purposes. So which solution is the most acidic? So you have a strong acid and two weak acids, and it turns out the strong acid. So remember, HCl, HBr, HI are strong acids. Nitric, sulfuric, perchloric, those are all the strong acids. Hydrofluoric is not on the list, it's a weak acid. So another way to look at the strength is to look at the percent ionization. So a strong acid is 100%. Weak acids, though, have different percent ionizations, and depending on the strength of the weak acid, they will disassociate to different amounts. And the higher the percent ionization, the stronger the acid. And the relationship between initial between the hydronium and initial concentration, increasing the initial concentration means that you're going to have more hydronium ion equilibrium. Not surprising. So if you increase the reactants, you have more products. So that's just Le Chatelier's principle. And it also means that you get a slower increase in acid concentration, but as you add them. So that's one thing with the weak acids. So the equilibrium of weak acids, so the concentration of hydronium ions increases, but the percent ionization decreases. And this is also, you could argue, with Le Chatelier's principle. So, find the pH of mixtures of acids. So, for a strong acid and a weak acid, the strong acid has completely breaks apart. And oftentimes, the weak acids is usually negligible, with the exception of sulfuric acid. And sulfuric acid, that actually has a pretty strong weak acid, so that's a little more difficult. So, generally speaking, you just need the stronger acid to consider, and this also works for polyprotics, with the exception being, of course, sulfuric. So that one's a little more difficult. So strong base. So stronger the base, the more willing it is to accept hydrogen ion. And so for ionic bases, pretty much it just breaks apart into hydroxide. And these are strong electrolytes. And multi-hydroxide strong bases just break apart in one step as well. And the POH is 10 to the minus POH is equal to the hydroxide ion concentration. So weak bases, only a small fraction accept hydrogen ions. So these are the weak electrolytes, and they have an equilibrium usually very, very small. They mostly stay molecular. So and similarly, acids, you have to use an ICE chart. So for doing the base ionization constant for weak bases. So this one, of course, is look at the equilibrium. This is the reason why we're doing this chapter after equilibrium, so it's nice and fresh in your mind. So here's some common weak bases that you see, and then the relative size of their Kb values there. So structure of amines. So these are, although ammonia is not really an amine is a nitrogen-containing organic compound. These are various amines, and they're also weak bases. So finding the hydroxide concentration and pH of weak bases. Same idea for the acid. Use the initial change equilibrium table, and then put in the values, and then find the calculated value of X. So X being the extent of reaction from the ice table. And then, of course, one of the different steps, though, when you do the base, you're calculating the hydroxide ion concentration. So keep that in mind, that from that you can get the POH, but you get that extra step. So 14 minus the POH gives you the pH. We usually list things in pH instead of POH. So acid-base properties of ions and salts. So salts are ionic compounds, so metals and nonmetals, and they form ions. So I always think of it this way. So the cation of a strong base and an anion of a strong acid, these don't ionize in water, but then you have the weak acids and weak bases. These do react with water. So if you have a strong acid with a weak base, then you get a acidic salt. If you have a strong base and a weak acid, then you have a basic salt. Because I see that this base is so strong that it makes a salt shift on one side. So, of course, when you have a weak acid, weak base, you can't tell that right away. Well, a strong acid and strong base make neutral salts. But a weak base, weak acid, it depends on the size of the equilibrium constants, which way it shifts. But a strong acid and a weak base makes an acidic salt. A strong base and a weak acid make a basic salt, alkaline salt. So the answer why is because of the hydrolysis reaction of the conjugate base. So a little bit of caution, though, also for sulfuric acid, HSO4 minus, that is a weak acid. So that is not, well, it is the conjugate base to sulfuric acid, but that's actually a fairly strong acid. So that's a bit of an exception to the rule. But the anion to the acid is a weak base. So it'll shift the equilibrium. If you have to put it in water, it will shift the equilibrium. So here are the relative strengths of the acid-base pairs. And relation between Ka and Kb, well, Ka times Kb, this equals Kw. So so if you, and this is for the acid and conjugate base, or base and conjugate acid. So if you want to know what the value is of the other, you can do it by multiplying them together to form Kw. And this is at 25 degrees Celsius. Of course, this is still the same relationship for non-standard conditions, not 25 degrees Celsius, but then the Kw value changes. So which anion acts as a weak base? So remember your strong acids, HCl, HBr, HI, those are all strong acids. HF is not a strong acid, so that means that the weak acid is the one, anion here is a weak base. So, and cations can also be weak acids, so meaning you have a strong base, so like an alkali metal cation, so like iron chloride, for instance. So, well, I should say alkali. That's a halide. So something like iron chloride. Then the iron plus 2 or plus 3 is actually going to be a weak acid. But something like ammonia will react with water. So the idea, though, is that cation is reacting with water via the hydrolysis reaction to turn it into a weak acid. So cations of certain metals, they also can form complexes with water, and these complexes can actually themselves become weak acids. So classifying solutions as acidic, basic, or neutral, and I mentioned this before. If you have a strong acid, strong base, neutral solution. And the bases for strong bases, these are the alkalis and alkaline earths. So alkaline earths are considered strong bases for this. And then you already memorized the strong acids. So these ones form neutral solutions. But if you have a strong base and a weak acid, so if you've memorized the strong acids, all the other acids are weak acids. The salt of a strong base and a weak acid, these are all alkaline. And again, I know this, it's really from the hydrolysis reaction, but I see it as the base being so strong, it makes the salt basic. And same thing with the conjugate acid, it will form an acidic solution. So if you have a weak base and a strong acid, then the counterion is acidic. And for the same reason being. And what about if you have weak acid, weak base? You don't know. You have to look up the relative values. And for ammonium fluoride, the equilibrium is higher for hydrofluoric acid than it is for ammonia. Therefore, the solution is acidic. So here's a chart to explain what was mentioned. Which ionic compounds forms an acidic solution when dissolved in water? So which one is a strong acid, weak base? It's the first one. So polyprotic ions, acids, many protons, they have different Ka values. So the first hydrogen is Ka1, second hydrogen is Ka2. If there's a third hydrogen, it's Ka3. There's a fourth hydrogen is Ka4, and so on. So, for most problems, you can just use the first ionization. The exception is sulfuric. And usually the second and third and fourth are negligible. It turns out for sulfuric it's not. So sulfuric is a is a problem when you have to calculate those. So here are some common polyprotic ones, and the subsequent Kas are not an issue, with the exception of sulfuric acid if you have the solution. But if you have various salts, though, these Ka values are good to know. And here's some more. So ionization of sulfuric acid, you have two Ka values. First one strong, the second one 1.2 times 10 to the minus 2. And the second ionization you have to account for. So when you do these problems, it's just like the common ion effect. What is a common ion effect? Include the bisulfate ion and hydronium ion and the initial concentrations going forward. So dissociation of a polyprotic acid. The first one breaks apart, and the second one and the third and fourth were applicable. But typically speaking, for this acid, the second dissociation constant is 10 to the 9 times smaller, so it's negligible. So find the pH of a polyprotic acid, write the ionization of the acid, and prepare the initial change equilibrium ice tables. And then put in the values and show the shift and include that, and then from the amount of hydronium and the different reactions. And like I said, what you'll find is everything except for sulfuric. It's only the first one. So it's the same idea solving these as you've seen with the monoprotic acids. So what is the ion concentration of weak diprotic acid? So really what you find out is that it's just the first hydrogen. Although these values are important to know, because sometimes you'll get a salt that has something like TSP, trisodium phosphate. So that's Na3PO4 minus. So when you look at the pH of this solution, you have to do the hydrolysis reaction. So it's important to know the different values of the equilibrium constants for things like that. So binary acids, the stronger the bond with the hydrogen, the weaker the acid. So the stronger the bond is, the weaker the acid. Or weaker the bond, the stronger the acid. And there is the general trend going there. So for oxyacids, adding more oxygen draws more electron density away from the hydrogen-oxygen bond, and that weakens that bond, which makes it a stronger acid. So generally speaking, the more oxygens in the oxyacid, the stronger the acid. And they tend to increase to the right across a period. So carbonic acid, for instance, is greater than boric acid. And bond strength and acidity, you can see here the different bond strength. As the bond energy gets lower, the acid gets stronger. And electronegativity difference, also you can see that the bigger difference in electronegativity, so the greater the difference is, the more electron density you pull away from the hydrogen, therefore making it a more acidic bond. Adding more oxygen, and oxygen is the second most electronegative atom as well, pulls more of the electron density away from the hydrogen, making it a stronger acid with the more oxygens. So which one is more acidic? The carboxylic acid, so methanol or formic acid. Naming the word formic acid there. Which one is more acidic? Obviously it's formic acid, hence the name. But this one has more oxygens. So I mentioned before, Lewis acids and bases. Lewis acid accepts electrons. Lewis base donates electrons. These types of reactions do not require hydrogen to describe. So it has to do with electron deficient. The acids are electron deficient, and the bases are electron rich. So that is one way you can look at doing the acid-base chemistry, is where the electrons go. And this is the best way to describe it, actually, is where electrons are flowing. And same idea, Lewis bases. Lewis bases are electron rich, and they're able to give their electron density away, making them Lewis bases. And generally speaking, though, the more electronegative an atom it is, the less likely it is going to be a Lewis base. So because electronegative atoms draw electron density away towards themselves, it's harder to get those atoms to give up electron density. And Lewis acid-base reactions, these react by donating, the base donates electrons density to the acid, and it forms a product called an adduct. And so all Arrhenius acids are Bronsted-Lowry acids. All Bronsted-Lowry acids are also Lewis acids, but not all Lewis acids involve hydrogen. So you can see, so one here, for instance, or actually two here. You can see two. There's two here. These are acid-base reactions, but they're not. The Arrhenius or Bronsted-Lowry theories do not describe these reactions. So, for instance, you can form Lewis acid, Lewis base to form a adduct. Well, also I could call it a complex as well. So many different things. And then water and carbon dioxide form carbonic acid as well. So that's another one. So fuel, one thing with carbon dioxide, we get quite a bit of our energy from burning fossil fuels. So this is not just electricity; it's also for transportation. And with the but many sulfur is found, like quite a bit of coal. So sulfur is also released in the combustion. Also, nitrogen, because of in the internal combustion chambers of cars and whatnot, you can form nitrogen oxides. The problem with sulfur oxides and nitrogen oxides, it can turn into acid rain. So, but here we show the energy consumption by source in 2017. But then the acid rain can form. So there's various sources of natural acid rain. So carbon dioxide in the atmosphere automatically makes water acidic. But anything below a pH of 5.6 is considered acid rain. So sulfur oxides, so volcanoes, for instance, are a very big source of sulfur oxides. And lightning strikes can also form nitrogen oxides. Of course, sulfur and nitrogen can come from anthropogenic human made, and also bacterial action can generate nitrogens as well. But the anthropogenic source, human sources, can increase the acidity of rainwater, and this is an issue for structures and also plant life. So living in Hawaii, there's a volcano there. The plants are used to that acidic rain. But in other areas, plants are not used to it. So if humans come in and then they release the pollutants that cause acid rain, it can greatly damage the biosphere in that area. So here's the pH in different areas, and has been measured. And so acid destroys metals. It also destroys things like carbonate, so marble and also cement. So that will destroy that. Also acidify lakes and changing the soil. So it can wreak havoc on the biosphere. So here shows the structures going away, and also can kill trees or various other plant life from the acid rain. And the Clean Air Act, as well, it's passed in the 1970s, but there's been updates to them and reduce in the sulfur dioxide for various things, for utility, especially coal. And then this has greatly improved the air quality in the United States. So you can see that the air quality in the concentration of sulfur in the air has gone down. And thank you for listening, and join me for future